Consider the linear transformation f R2 to R2 that is a reflection of points in the plane through the line L mirror. That is, the line that makes an angle 1/2 alpha with the x-axis. So to break this down, we have a linear transformation f, which takes R2 to R2. So we know then that we can think about R2, which is this here. Then if we look at L mirror and work out what L mirror is, we can draw L mirror on our plane. L mirror is a parametric equation and it contains a variable here, alpha. So we need to define alpha so that we can draw this line. Alpha is defined down here. First consider the specific case with alpha equals pi/3. So we can put alpha into this equation. So now when we place pi/3 into this equation and then simplify and then use the unit circle to solve the cosine and sine, which you'll see is right here, you will end up with this value here for L mirror. Now we draw L mirror on our plane and we get this line right here. So now we can imagine what this linear transformation will do to a point in R2. So our linear transformation will take a point and it's going to reflect it across this line. So imagine we've got a point, say right here. We put it through this linear transformation, it's going to reflect across this line and we'll get a point about here. Now that we have some idea of what this linear transformation does, we can continue with the problem. So find a vector W that is orthogonal to L mirror and use projections to determine f of E1 and f of E2 for the standard vectors E1 equals 1, 0 and E2 equals 0, 1. So the first part of this question, find a vector W that is orthogonal to L mirror. What that's asking us to do is discover any vector and we'll call it W that is orthogonal to L mirror. And orthogonal means perpendicular. When two vectors are orthogonal, or those two vectors are perpendicular, the dot product of the two vectors will equal 0. So how does that help us? Well, we're trying to find a vector W that is orthogonal to this line. So this vector here will be perpendicular to this line here. Now, we know this equation here is true when U and V, these two vectors, are orthogonal. So if we find any directing vector of L mirror and we find the dot product of some vector W, and that equals 0, then we know that W is the orthogonal vector of L mirror. So we need to find a directing vector of L mirror. So to do that, we take our parametric equation, which is right here, and we replace lambda with a real number. Now, I've dropped in 2, and that just makes this equation nice and easy. We then use scalar multiplication, and we end up with L mirror equals the square root of 3, 1. So now we need to solve for W. W could be a whole bunch of different vectors. So we can just set a single value of W, W1 or W2, and then solve, and we'll get a vector which is orthogonal to the directing vector that we found of L mirror. So now I need to solve for W. I need to pick one point in W and just pick a point. So I'm going to let W1 equal 1, and then I can solve for W2, which then gives me the value of W, which in this case is 1 negative the square root of 3. Now we can draw W, and you can see that it's definitely perpendicular. It's definitely orthogonal to our line. So we've found a vector W that is orthogonal to L mirror now. There are plenty of other vectors that are orthogonal to L mirror, but we just needed to find one, and we found one. So now the second half of the question, use projections to determine f of E1 and f of E2 for the standard vectors E1 and E2. So what does that mean? Well, let's start by drawing E1 and E2 first. So E1 looks like this here, and E2 looks like this here. So there's E1 and E2. So if we return to the question now, how do we determine f of e1 and f of e2. So this is what we need to find, the answer to f of e1 and the f of e2. How do we find those values? So f is a linear transformation. It reflects points across our mirror. So if we look at our two-dimensional plane again, we can see that here's our line and here are our points. So if we take one of these points and we put it through this linear transformation, we'll get a reflection on the other side of this line. So that's great. We know what we're aiming for now, but how do we get there? Well, they give us a hint right here. Use projections. So what do they mean by this? What is a projection? Well, a projection is this. We're going to project a vector onto another vector, and we can use this formula right here to do that. So if we take this formula and we want to project E1 onto our mirror, then E1 would be U in this formula, and our mirror would be V. And then if we plugged in E1 in our mirror, then the answer that we would get would be 3 over 4 and the square root of 3 over 4. Now, if we draw this on our graph, we can see right here this projected vector. So that is the line of E1, or the vector rather of E1 projected onto our mirror. Now what we can do is work out the distance between E1 and our new projected vector. And then this distance here, if we double it and add it to the other side, we will find out what E1 is when you pass it through a linear transformation. So let's find the difference. So we take our projected vector, subtract E1, and we get this new vector here. Now, this vector looks like this right here. Imagine if you added this vector to the end of E1, you'd get back to this projected vector. Now, if you added that vector again, then you would find the reflection of E1 over this line. So that just looks like this. We have E1 plus 2 times that difference vector equals this vector right here. And this vector is this one right here. Now, this is the reflection of E1 over this line. This is the answer to f of E1. So now we've found W, we've found f of E1, and all we have to find is f of E2. But I'll leave that one up to you. You can see if you can work it out yourself, doing the exact same method as we've just done to find f of E1.